My name is Nico, and you're watching Frontline Reports, where we go beyond the headlines to bring you the stories that are quietly rewriting the future. Close your eyes for a moment and picture this. You are standing on a rooftop somewhere in Shanghai. Below you, the city has ground to a complete standstill. Thousands of vehicles stretch bumper to bumper across every visible road and intersection. An endless metallic river that hasn't moved in 40 minutes. Car horns fill the air in overlapping waves of frustration. A commuter on the street below glances at their phone, then at the traffic ahead, and lets out a long, slow breath. They left home an hour ago. They are still 12 blocks from the office. The air is thick with exhaust and heat. Now look up. Above the rooftops in the haze, something is moving. It cuts through the sky with a kind of quiet, electric authority that does not belong to any aircraft you have seen before. It is not an airplane. It has no wings in the conventional sense. It is not a helicopter. It is far too sleek, too aerodynamic, too precise in its movement. It looks, if anything, like the kind of vehicle that a science fiction author in the 1970s might have sketched when imagining what the year 2050 would look like. Clean lines, multiple rotors, electric propulsion, silent enough to make you question whether it is real, but it is real. It has already been tested, at speeds exceeding 360 kilometers per hour. Welcome to Frontline Reports. My name is Nico, and today we are going to tell you the full story of one of the most extraordinary technological developments of our generation, China's flying car. Not as a concept, not as a prototype gathering dust in a research laboratory, but as a vehicle that has been built, tested, pushed to its performance limits, and is now on a pathway toward commercial reality that is closer than most people realize. This is not hype. This is not science fiction. And by the time this story is done, you will understand not just what has been built, but why it matters, who is competing to own this space, what obstacles still stand in the way, and what a world with flying cars might actually look like for the billions of people who currently spend a staggering portion of their lives sitting in traffic, going nowhere. Before we can appreciate the significance of what China has built, we need to spend a moment honestly confronting the scale of the problem it is trying to solve. Because that problem, the problem of moving human beings through the modern world efficiently, cleanly, and without the crushing economic and environmental costs of current transportation systems, is far larger and far more consequential than most people who have never studied it carefully tend to realize. Transportation has been one of the defining civilizational challenges since the Industrial Revolution began driving massive human migration from rural areas into rapidly expanding cities. Cities were not designed for the density of people and vehicles that the 20th and 21st centuries have poured into them. They adapted, awkwardly and expensively, through the construction of highway systems, urban expressways, subway networks, and bus corridors, all of which provided relief for a time before demand outgrew capacity and the cycle of congestion resumed. The scale of the current situation is genuinely staggering. In 1900, just 125 years ago, fewer than 10,000 automobiles existed in the entire world. As recently as the 1950s, car ownership was still a relative luxury confined largely to wealthy Western countries. By 2023, there were more than 1.4 billion registered motor vehicles operating on the planet's road networks. That is roughly one vehicle for every 6 people alive today. And the number continues to grow, driven by rising incomes in Asia, Africa, and Latin America, where hundreds of millions of people are entering the middle class and purchasing their first vehicles. The consequences of this explosion in vehicle numbers are felt every single day by hundreds of millions of commuters across every major city on Earth. Research conducted by the Texas A&M Transportation Institute, one of the most respected authorities on traffic behavior and its economic consequences, found that American drivers alone lose an average of 54 hours per year to traffic congestion. That is more than a full working week, simply evaporated sitting in stationary or barely moving vehicles. In the most congested American cities, particularly Los Angeles, that figure climbs above 100 hours annually, more than 4 complete days of a person's life every year lost to gridlock. And in the megacities of Asia and the developing world, the situation is considerably worse. Drivers in Mumbai, Jakarta, Bangkok, and Bogota face some of the most severe urban congestion on Earth, with average commute speeds in dense urban cores sometimes falling below 10 kilometers per hour, slower than a brisk bicycle ride. In some cities, the economic calculation of whether to own a car at all is being questioned, not because people do not want the convenience, but because the time lost to traffic now genuinely rivals the time saved compared to walking. The financial cost of this global congestion crisis is not a rounding error. The total global economic impact of traffic congestion, accounting for wasted fuel, lost working hours, supply chain delays, increased transportation costs for businesses, and the healthcare burden of stress and air pollution-related illness, is estimated to exceed $2 trillion per year. $2 trillion. Annually. That is money that could fund hospitals, schools, clean energy infrastructure, and research programs. Instead, it is burned, quite literally, in idling engines and wasted hours. And then there is the environmental dimension, which adds another layer of urgency to the search for transportation alternatives. According to the International Energy Agency, the global transportation sector, cars, trucks, buses, ships, and aircraft combined, is responsible for approximately 37% of all carbon dioxide emissions from energy use worldwide. Road vehicles alone account for the largest share of that figure. The private automobile, which transformed 20th century life in so many positive ways, has also become one of the single largest contributors to the climate crisis threatening 21st century civilization. This is the problem, the full, uncomfortable scale of it. And for decades, engineers, entrepreneurs, urban planners, and governments have been asking the same fundamental question. What if the solution was not to build more roads, which has been proven repeatedly to simply attract more traffic, but to take transportation off the roads entirely? What if the sky above our gridlocked cities could become a usable transportation network? What if human beings could move through 3 dimensions rather than being constrained to the 2-dimensional surface of roads that were designed for a world that no longer exists? That question has been asked since the dawn of aviation. What has changed is that the technology to answer it seriously, finally, genuinely, at commercial scale, has arrived, and China is leading the race to build it. China's emergence as the country at the frontier of flying vehicle development is not a coincidence. It is the product of a deliberate, sustained, and extraordinarily well-funded national commitment to dominating the transportation technologies of the future, a commitment that has already produced results that have reshaped the global transportation landscape once before. Consider what China has already achieved on the ground. China operates the world's largest high-speed rail network by a considerable margin. More than 45,000 kilometers of dedicated high-speed track connects cities across the country, carrying passengers at speeds of up to 350 kilometers per hour. This network, which barely existed 20 years ago, is now so deeply integrated into Chinese daily life that hundreds of millions of people use it as casually as Americans use highways. It has compressed distances between major cities, restructured regional economies, and demonstrated something important about what is possible when a government with sufficient resources and political will commits to infrastructure transformation at scale. China is also the undisputed global leader in electric vehicle production, adoption, and, increasingly, technology. Chinese manufacturers now produce more electric vehicles each year than the rest of the world combined. Chinese battery manufacturers, particularly CATL, supply a significant portion of the global EV industry's power storage needs. Chinese EV brands, BYD, NIO, Li Auto, and others, have grown from domestic curiosities to legitimate global competitors challenging established Western and Japanese automakers in markets across the world. Against this backdrop, it is perhaps not surprising that China has also set its sights on the next frontier of transportation, the sky above the gridlocked streets. The company at the center of this story is XPeng Aero HT, a subsidiary of XPeng Motors, one of China's most technically advanced and internationally recognized electric vehicle manufacturers. XPeng Motors was founded in 2014 and built its reputation on sophisticated software integration and autonomous driving technology that drew frequent comparisons to Tesla. The company's vehicles were never just cars in the conventional sense. They were software platforms that happened to have wheels, designed around the assumption that intelligence and connectivity were as important as horsepower and fuel efficiency. XPeng Aero HT carries that philosophy into an entirely different domain. Its mission, stated clearly and pursued with the financial backing and manufacturing infrastructure of an established automaker, is to build vehicles that are genuinely dual-domain, capable of operating on roads and through the air, in a form that is commercially viable, not just technically impressive. Their flagship development is the Land Aircraft Carrier System, a name that is either brilliantly descriptive or slightly grandiose depending on your perspective, but that captures something real about the concept's ambition. And the performance figures attached to this system are not marketing embellishment. They are the results of actual flight testing conducted in controlled airspace, documented and independently observed. The flying module of the Land Aircraft Carrier System has been tested at speeds exceeding 360 kilometers per hour in level flight. Let that number sit for a moment before we move on. 360 kilometers per hour. That is the same speed at which China's fastest commercial high-speed trains travel. It is more than 3 times the legal speed limit on most major highways anywhere in the world. A journey by car that might consume 2 hours of frustrating stop-and-go urban driving could, at that speed, be completed in under 30 minutes from point to point. The productivity, economic, and quality of life implications of that kind of speed reduction in daily commuting are difficult to fully quantify. But they are profound. At this point in any story about flying cars, there is a real risk of losing a significant portion of the audience to the dense forest of technical terminology that surrounds aviation engineering. Terms like eVTOL, distributed electric propulsion, fly-by-wire control systems, and rotor blade pitch management can turn even genuinely curious viewers into people who are suddenly very interested in checking their messages. So let us take a deliberate step back and explain the technology in terms that make it accessible. Because what has actually been engineered here is genuinely fascinating, and understanding it makes the achievement significantly more impressive. The fundamental category of aircraft that XPeng Aero HT's flying vehicle belongs to is called an eVTOL, Electric Vertical Takeoff and Landing Aircraft. The name is almost entirely self-explanatory once you break it down. Electric, powered by electric motors and batteries rather than combustion engines. Vertical, capable of rising straight up from the ground without needing a runway. Takeoff and landing, able to return to the ground in the same manner, descending vertically to a small designated pad rather than requiring an extended runway for deceleration. Think of it, at the most basic conceptual level, as a dramatically more sophisticated and much larger version of the consumer drones that have become familiar sights at outdoor events, on film sets, and in public parks over the past decade. The underlying physics, rotating blades generating lift, are related. But the engineering complexity, safety requirements, payload capacity, and performance characteristics are in an entirely different league. Traditional helicopters achieve vertical flight through the same rotational lift principle, but they are powered by combustion engines, which are mechanically complex, maintenance-intensive, extremely loud, expensive to operate, and fundamentally incompatible with the environmental and economic requirements of mass urban transportation. A conventional helicopter requires highly trained specialist pilots, extensive maintenance schedules, and operating costs that place it firmly in the category of emergency services, luxury transportation, and military applications, not everyday commuting. What the eVTOL revolution has accomplished is to rebuild vertical flight from the ground up using technologies that did not exist, or did not exist in adequate form, when helicopters were first developed. Modern high-efficiency electric motors that convert electrical energy to rotational force with far less waste than combustion engines. Advanced lithium battery chemistry that packs sufficient energy into manageable weight and volume. Sophisticated computer-controlled flight management systems that can make thousands of micro-corrections per second to maintain stability, far faster and more reliably than any human pilot could manually manage. And lightweight composite materials derived from aerospace and motorsport research that provide structural strength without the weight penalty of traditional metal construction. The specific design approach that Xpeng AeroHT has developed for the land aircraft carrier system is what engineers and industry analysts identify as its most distinctive and potentially most commercially significant feature: modularity. Rather than designing a single integrated vehicle that attempts to be both a capable road automobile and a capable aircraft simultaneously, a compromise that historically produces something that does neither job particularly well, Xpeng AeroHT's engineers separated the two functions into two distinct and independently optimized components. The first component is the ground carrier vehicle. This is a full-featured, comfortable electric automobile, capable of carrying passengers in normal conditions, equipped with advanced driver assistance systems, and able to operate on conventional road infrastructure without any special requirements. It looks from the outside like a well-designed premium electric car. It drives like one. It charges at standard electric vehicle charging infrastructure. The second component is the detachable flying module. This sits on top of the ground vehicle when not in use, carried in the way an aircraft carrier carries its jets, hence the name. When the operator decides to transition from ground to air travel, the flying module separates from the carrier, lifts off vertically, and transitions into forward flight. The flying module features 6 rotors arranged in a configuration specifically engineered to provide both the powerful lift required for vertical takeoff from a standstill and the aerodynamic efficiency required for sustained high-speed forward flight. Those rotors can tilt and adjust their angle dynamically during flight, allowing smooth transitions between the hovering phase of takeoff and landing and the forward flight phase of cruising. The flight management computer, running continuously during operation, makes constant micro-adjustments to rotor speed, pitch, and tilt angle to maintain stability in variable wind conditions, compensate for passenger weight distribution, and execute navigation commands. The brilliance of the modular design is that it eliminates the core engineering compromise that has defeated most previous attempts to create a practical flying car. By separating the ground and air functions into 2 distinct components, the engineers could optimize each one for its specific domain rather than accepting the mediocrity that comes from forcing a single vehicle to serve incompatible design requirements simultaneously. The ground vehicle is designed to be an excellent automobile. The flying module is designed to be an excellent aircraft. Neither one has to sacrifice its core performance to accommodate the other's requirements. In terms of energy storage, the system uses high-density lithium battery packs, specifically engineered to aviation-grade specifications. With thermal management systems, structural protection, and redundancy features that go significantly beyond what automotive-grade batteries require. Current flight endurance on a full charge runs between 35 and 50 minutes of continuous flying, with a practical range of approximately 200 kilometers in the air. Those figures are expected to improve meaningfully as battery energy density continues its documented trajectory of improvement. A trajectory that has already delivered enormous capacity gains over the past decade and shows no sign of plateauing. The redundancy systems built into the flying module deserve particular attention because they represent one of the most important engineering decisions in the entire design. If any single motor or rotor system experiences a failure during flight, the remaining systems are programmed and physically configured to compensate, redistributing the load, adjusting rotor speeds, and maintaining controlled, safe flight despite the failure. This kind of multi-layer redundancy is a fundamental requirement for any aircraft intended to carry human passengers over populated areas, and it reflects the depth of engineering investment and aviation industry expertise that has gone into making this vehicle viable for commercial operation rather than just impressive in test conditions. A vehicle can be impressively engineered in a design studio and still fail catastrophically when exposed to the real world. The history of transportation technology is littered with concepts that looked revolutionary in renderings and prototypes, but that could not survive the testing phase. So what has actually happened when XPeng Aero HT's flying vehicle has been put through its paces in real flight conditions? The results have been genuinely significant and increasingly public, which matters in an industry where extraordinary claims without extraordinary evidence should always be approached with skepticism. The company's earlier model, the X2 flying vehicle, was chosen for a high-profile public demonstration flight over Dubai in October 2022. The choice of Dubai was deliberately symbolic. The Emirate has positioned itself as one of the most aggressive early adopters of aerial mobility technology in the world, with its government actively working toward the introduction of air taxi services as part of its broader smart city ambitions. The Dubai demonstration lasted approximately 90 seconds in a controlled flight path, but its significance lay less in the duration than in the fact that it was conducted openly, in front of journalists and observers, with an operational vehicle rather than a concept model. The X2 flew. It landed. The technology worked. Since that initial public milestone, XPeng Aero HT's testing program has advanced substantially in both ambition and rigor. Engineers have conducted what the aviation industry calls envelope expansion testing, the systematic process of pushing a vehicle progressively closer to its theoretical performance limits in controlled conditions, gathering data at each stage before proceeding further. Speed runs conducted in controlled Chinese airspace over flat terrain produced the headline figure of 360 kilometers per hour in sustained level flight, surpassing the cruising speed of conventional commercial helicopters, which typically operate between 220 and 270 kilometers per hour, and exceeding the top speed of small Cessna-class propeller aircraft, which generally cruise at 200 to 230 kilometers per hour. The XPeng Aero HT flying vehicle, in its current test configuration, has already outperformed both categories of existing aircraft that it is most directly compared to. The company has also released documented footage of the vehicle conducting autonomous navigation testing, flying pre-programmed routes through designated airspace without any human pilot input, relying entirely on onboard sensor arrays, GPS navigation, and the flight management computer to execute planned flight paths. The implications of successful autonomous navigation testing are considerable. A vehicle that can fly itself is not merely a convenience, it is a fundamental enabler of the scalable air transportation system that proponents of urban air mobility envision. Aircraft that require trained human pilots will always be limited by the supply of pilots and the cost of their training and compensation. Vehicles that can navigate autonomously can be deployed at the scale that urban transportation networks require. In early 2024, the company announced that it had begun accepting pre-orders for the Land Aircraft Carrier System, a commercial signal that carries real weight because it indicates that actual customers with actual money are willing to commit to this technology before it is available. Pre-orders are not guarantees. They do not mean the product is ready to deliver, but they represent a level of market confidence that distinguishes a commercially viable technology from an impressive demonstration project. XPeng Aero HT is not operating in an empty field. The race to develop practical, commercially viable eVTOL aircraft and establish leadership in what the industry calls urban air mobility has attracted some of the most well-resourced and technologically sophisticated organizations in the world. Understanding the competitive landscape is essential to understanding both the significance of what XPeng Aero-HT has achieved and the challenges it faces in translating technical performance into market leadership. In the United States, Joby Aviation has emerged as arguably the most credible Western competitor in this space. Founded in California and backed by investors including Toyota and the United States Department of Defense, an investor combination that speaks to both the commercial and strategic significance of the technology, Joby has raised over $2 billion in funding and has completed thousands of test flights with its eVTOL aircraft, a 5-seat tilting rotor design with a fundamentally different configuration from XPeng Aero-HT's modular system. Joby has been working toward Federal Aviation Administration certification for commercial passenger operations, positioning its aircraft as an air taxi service for urban and suburban routes. The company set its own speed record in 2021 when its aircraft reached 336 kilometers per hour, a benchmark that XPeng Aero-HT's more recent testing claims to have surpassed. Archer Aviation, another California-based company, is pursuing a different market position with its Midnight aircraft, a 4-passenger eVTOL specifically optimized for short urban hops of 60 kilometers or less, the kind of SITE